Hello everyone, welcome back to the Math Fun Room. In this video we're going to talk about representing a function as a power series. Now up to this point throughout this whole chapter we have talked about series, specific types of series where we use alternating series test or integral test, comparison test, limit comparison test to look at the series and test for convergence. In the prior video, we discussed looking at a series, power series actually, and determining where it converges, its interval of convergence, and thus its radius of convergence. Now that prior conversation will follow us through this video as well, but we are going to focus a little further on the function and its power series. Okay, so I like to come back to start off this conversation using the geometric series, and that is typically what this conversation circles around, but I want to also use the sine series because we have done that in a couple prior videos. Now, let's start with the series 1 plus x squared plus x cubed plus dot dot dot. All right, based on our prior conversations, and in particular the one in section 11.2, this is a geometric series. Right? So we can see that if we take this first term of 1, multiply by x, we get the next term. And then we take that term, multiply by x, we get x squared. Take x squared, multiply by x, we get x cubed. So this is geometric, and the common ratio is the x that we multiply by. So we could write this as, so remember that a geometric series we could write as ar to the n minus 1, where n goes from 1 to infinity. We can also write that as ar to the n, as n goes from 0 to infinity. Personally, this is the form I prefer, n starting at 0, and that's what you're going to see classically in a section like this in any calculus textbook. So the a, if I look at this last expression, ar to the n, the a is the first term in the series. So this series here, in sigma notation, the first term in the series is 1, and then I have x to the n, and n goes from 0 to infinity. So in a sigma notation form of my series, right, here is 1 plus x squared plus x cubed plus so on and so forth. All right, now the reason that we start with this series is we know how to identify it as geometric, and we know how to discuss where it converges. All right, in particular, we know that every geometric series converges when the common ratio is less than 1. So this converges when the common ratio in absolute value is less than 1. So for us, that means our ratio is x. So this will converge anywhere between minus 1 to 1. Right? So this implies minus 1 to 1. In an interval and an inequality form. We could also write that in interval notation. All right, so knowing that's geometric, we can jump right to where it converges. Now what we could do, and I won't take the time to do it here, but what we could do is we could use the ratio test. So we could come back to our closed form of our series, the sum of x to the n as n goes from 0 to infinity, and we could use the ratio test. And in fact, we did that in the prior video. So feel free to go back and take a peek at that. Now the conversation in this section is what we'll discuss now. So if I take a look at this geometric series, we know that the sum of a convergent geometric series is a over 1 minus r. Now again, a being the first term in the series, which we can see a is 1, and then r being the common ratio, which we know is 1 over 1 minus x. So what we're going to do in this case is phrase the conversation in the following manner. This function, 1 over 1 minus x, has this geometric series representation. And then we'll go ahead and write it in the closed sigma notation here. And we know that that is true for any x between -1 and 1. So instead of, let me kind of re-summarize here. Instead of saying the series 1 plus x squared plus x cubed plus dot dot dot, instead of saying that series has a sum of 1 over 1 minus x, we're going to rephrase this, and we're going to say this function 1 over 1 minus x has this power series 1 plus x squared plus x cubed. So in the next couple videos, what we want to do then is ask ourselves which functions have power series, and whichever ones do have power series, what are those power series representations? All right, now I want to focus a minute just graphically. So let's recall, I don't want to recall that back in a prior video, I forget which one it is, we had told ourselves, or we were told, that the sine function has a power series, and the power series is of the form -1 to the n over 2n plus 1 factorial times x to the 2n plus 1. So when we wrote this out, this was x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, or minus x to the 7th over 7 factorial, plus dot, dot, dot. So in a prior video, we saw the sine series, and we just now have seen this series for 1 over 1 minus x. So we have two functions at this point that we know have a power series representation. Again, the conversation here is, well, do other functions have power series? The answer is yes, and we'll talk about why and how to develop those things. So what I want to do in a visual manner is talk about what these functions look like graphically. And I meant to write here. Remember, we actually, in the prior video, when we discussed the ratio test, well, I guess it was 2 videos ago, and it was the prior video too, right? We had used the ratio test on the sine series, and we saw it converged for all reals. Oops. Right? So all reals is where it converged. So what I want to do is pull up our graphing calculator Desmos, and let's take a look at this visually. All right, now way back in the beginning of this whole chapter, I brought up this graph to just kind of give us a little motivation, some foreshadowing. So when I'm in Desmos.com, I'm going to click the 3 little lines up on the left. I'm going to scroll down, and under the calculus topic is the Taylor expansion. So if I open that graph, this is going to actually give us the graph of the sine series. Now what I want to do, I want to change these limits because the a represents the n number, right? So n goes from 0 to a. All right, so I'm going to go from 0 to, let's say, 10. Right? That's really where I want to start. So let me back up to 0. All right, now let me come back to my Word doc. If I plug in, so if I'm looking at the sine series and I plug in n equals 0, that gives me this first term, right? -1 to the 0 is +1. 2 times 0 plus 1 is 1 factorial, and then x to the 1. So that gives me the first term. So in essence, sine of x is approximated by x. Now, I'm going to come back to Desmos, and that's what I'm graphing here. Notice this is the line y equals x, and then this is my sine function. So sine of x is approximated by x, and it's kind of when x is small. Right? So it looks like, almost like -1 radian to 1 radian. Sine x is approximated by x pretty well, actually. Now, think about what this means, right? The x is a theta value, so this is like sine of theta is approximated by theta. So the sine of, 1 radian is going to be approximately 1. Or the sine of half a radian is approximately 1/2. Now, the further I get from the origin, the worse the approximation is. All right, so pi is like 3.14, right? Here's pi, and I can see that the sine of pi is not approximated by x equals pi. That's a horrible error there. So we want this estimation to be better. So how do we make it better? Well, obviously, if I use the first two terms, I'm getting a better approximation. Just like area under the curve, right? When I use more rectangles, I get a better estimation of the area under the curve. So the more terms I use, the better my approximation is. Now, what we talked about in the prior section is that this series will converge for all reals. So let's see what that looks like visually. So as I add more and more terms, here's what I'm going to see. So if I add the next term, right, I have two terms, x minus x cubed over 3 factorial. So if I add the next term, and I go, so here's the 0th term and the first term being added. And we can see we have like a negative x cubed function. So here's my negative x cubed function. Notice that between y equals x and y equals x cubed, the convergence is a little bit further. Right? So for example, out here at like 2 radians, this was a really bad estimation. But when I add on the next term, I can see that error is much smaller there. So as I add on more and more and more terms, the convergence kind of spreads from x equals 0. So I'm going to stop right there. So this is adding up to n equals 9. So I'm going from n equals 0 to n equals 9. That's the first 10 terms in my series. So now we can see out here at x equals pi that this is an amazing approximation, and they're probably equal to each other or extremely, extremely, extremely close. We can analyze that a little bit deeper. I don't want to. I want to focus on the bigger conversation here. So in other words, if I plug x equals pi into sine, it is approximated by plugging x equals pi into this polynomial. This is a polynomial. These are x's with powers to them. So if I use the first 10 terms here, and I plug in pi for x, I plug in pi into the polynomial, those two things are going to equal each other. So, again, notice the interval of convergence was all reals, and as I add more and more and more terms, the sine function becomes, more and more hugged by that polynomial of terms, the power series. All right, now in our problem we started with here, our geometric series, the function 1 over 1 minus x has a power series representation, 1 plus x squared plus x cubed. So I'm going to come back to Desmos, so I'm going to type this in. So I'm going to replace f of x with 1 divided by 1 minus x. Then I'm going to replace the series with x to the n that we had there. I'm just deleting everything, x to the n. So there's that series. Now I'm going to go all the way back, and let me turn this off for a moment. So let me turn on projector mode. So here's my function 1 over 1 minus x that I'm graphing. Now, just like we talked about with the sine function, if I use the first term in the series, which is 1, this is an approximation to 1 over 1 minus x. And we're going to notice in this case that when I look at just the first term, this is a really bad approximation. Right here at x equals 0, it's a good approximation. Just a little to the right and left of 0, it's okay. But as I move further from 0, it's really bad estimation, really bad error. So when I add more terms, right, 1 plus x is going to be a better approximation. 1 plus x squared is going to be an even better approximation. When I add the first 4 terms, that's an even better approximation. So as I add more and more terms, let's do that, my approximation gets better and better and better. And we can see our polynomial, our power series, converging to the function. All right, now notice something else different from the sine series. With the sine series, we said it equaled, right, our power series, our infinite sum, equaled sine x for all reals. This geometric series, 1 over 1 minus x, has a power series representation, and it's only valid between -1 to 1. So when I look at that graph, notice only between -1 to 1 in the domain, this power series is a great approximation to the function. But outside 1 and -1, it is a horrible approximation. So that is the visualization of the interval of convergence like we talked about in the prior video. So when we take a function like 1 over 1 minus x or sine x and we find its power series, it's really important for us to know where is that valid, right? Where does it converge? We are only interested in series that converge. Those are what's going to be meaningful to me. Series that don't converge are not going to be meaningful to me. All right, so coming back to what I said at the very beginning of this video is the conversation here is what functions have power series. So we know the function 1 over 1 minus x has a power series representation. It turns out to be geometric, 1 plus x squared plus x cubed plus ... We also know, only because I told you in a prior video, that sine x has a power series representation, and this is not geometric, right? But here's a power series representation, x minus x cubed over 3 factorial, so on and so forth. So again, this conversation is I have a function. Does it have a power series representation? All right, now the first thing that we're going to do here is some algebraic manipulation. So for example, let's say, and this would be kind of a typical homework question, we want to use a known series to find a series for a new function. Right? So my instructions will say something like this, right? Let's say use the known series. Use the known series for 1 over 1 minus x. So that's 1 plus x squared plus ... which is x to the n, as n goes from 0 to infinity. So this is a known series. We know this geometric series. We want to use that known series to find a series for the function f of x equals 1 over 1 plus x. All right, so initially in this conversation, the way that we're going to approach this is we're going to algebraically manipulate my known series. And what I mean by that is the following. I don't want to focus on the fact that this is the letter x. So what I want to think of is 1 over 1 minus u is equal to, this is equal to 1 plus u. I'm going to keep switching colors here, plus u squared plus u cubed, so on and so forth, plus ... Right? So that equals the sum of u to the n, as n goes from 0 to infinity. Excuse me. So whatever my letter is, 1 over 1 minus x is 1 plus the x squared plus the x cubed plus ... So when I have the function that I'm trying to find a power series for, 1 over 1 plus x, I have to connect back to my known series. So what I'm going to do is write this as 1 over 1 minus negative x. So by taking my function I'm interested in, 1 over 1 plus x, writing it in the form of my known series, then the negative x plays the role of my green u. So everywhere I have a green u, I'm replacing it with negative x, kind of like a u substitution in a way. So I have 1 plus negative x squared plus negative x cubed, so on and so forth. And that's going to be negative x to the n, as n goes from 0 to infinity. So I'm using my known form, 1 over 1 minus u, being 1 plus u squared plus u cubed. And I'm taking 1 over 1 plus x, and I'm manipulating it to look at it as 1 over 1 minus something, 1 over 1 minus u. All right, so the last thing I really want to do here then is just a little bit of cleanup. So let's take a look at our power series that we have written here, 1 plus negative x squared, so on and so forth. So we know this is representing the function 1 over 1 plus x. So, 1 plus negative x is the same thing as 1 minus x. When I square negative x, this is really negative x times negative x, which is positive x squared. And then negative x cubed is, again, negative x times negative x times negative x, which is going to be negative x cubed. So obviously when the exponent is even, I get a positive. When the exponent is odd, I get a negative. So we're getting an alternating series here. All right, and what I'm going to do is a little algebraic manipulation with my closed sigma notation. So I'm going to look at this for a moment. My negative x to the n, as n goes from 0 to infinity. And I'm going to write this. I'm going to use properties of exponents. Right? I'm going to write this as negative 1 times x to the n. And then I can write this as negative 1 to the n times x to the n. Right? So I'm just following properties of exponents there that allow me to take the product to a power and write it as the power of the products. I said that backwards. So the power of a product I'm writing as the product of powers. Now this makes sense, right? Because when I come back up here and look at my power series or my polynomial, this is alternating. So I have to have a negative 1 to the n to make this alternate, right? Just like we saw back in alternating series test. And then I have powers of x. Okay? So, let me just kind of connect all this back together. The function 1 over 1 plus x has a power series representation that is an alternating series. And that's equal to negative 1 to the n times x to the n. So we have 3 power series now. I want to phrase that the right way. We have 3 functions that have a power series representation. One of them is 1 over 1 minus x, one of them was sine x, and now one of them is 1 over 1 plus x. All right, now I'm going to do a couple more of these, and actually I'm gonna stop talking here for a minute, and I want you to do the next one for me. So what I want you to do here is use this prior example, use this prior function 1 over 1 plus x as now it's known. So let's say this is known, and what I want you to do is use this, right? This is known. So let's find a series for the function. Let's say 1 over, let's say 1 plus 3x. So I want you to pause the video for me and find the power series for this function. And when you're done, unpause and we'll come back and do it together. All right, how did you do? Okay. I heard everybody at once, so I was a little confused. All right, so let's go through this together. So the function I'm looking at is 1 over 1 plus 3x. And again, I want you to keep in mind that what we're trying to match now is 1 over 1 plus something. So I'm thinking of this as 1 over 1 plus, and then my something is 3x. So this is what's replacing my quote-unquote variable in my known series here. So this is going to be 1, and then I have minus the x. I get minus 3x in this case. And then if I look back up here to my known series, I get plus the x squared. So that's 3x for our function that we're looking at now. And then I'm going to do minus the x cubed. So my quote-unquote x is 3x. And let's say plus dot dot dot. So in sigma form, I'm going to have negative 1 to the n and then my 3x to the n. So I'm coming back up to that sigma notation right there, negative 1 to the n, x to the n. So this becomes negative 1 to the n, 3x to the n. Now I can do some cleanup here. So let me stop. Did you get that far? All right, excellent. So let's do a little bit more cleanup. So I'm going to keep writing this. I want to keep making the connection to the function because that's the conversation in this section. So 1 is 1, and then 3x is 3x, and then 3x squared. Well, that's technically 3x times 3x, which is 9x squared. But I'm going to write it as 3 squared x squared, and I'll point out to you why I do that in a second. And then this is going to become minus 3 cubed x cubed, and so on and so forth. So we can see that that's still alternating, right? If I look at my sigma notation, I'm going to actually do the same thing with the 3x to the n that we did in that example a couple minutes ago. I'm going to write this as 3 to the n times x to the n, using a property of exponents there. So the reason that I didn't square my 3 and write 9 or cube my 3 and write 27 is because I wanted to see that that was 3 to the n, x to the n, as I wrote those terms out. All right, cool. We now have 4 functions and their power series representations. I could go into Desmos and graph these. I'm not going to, just because it's going to make this video really long if I do that. But I could graph 1 over 1 plus 3x, and then I could graph this sigma notation power series. So what I would encourage you to pause the video, open up Desmos, right? Go into that Taylor series graph here, and then change your function, change the form of your series, and see how that looks. All right, try that out, and then we'll take a look at another example. All right, now that you've unpaused the video, let's come back and take a look at another function that we're going to develop the power series for. Now, just to not get too crazy and have the video be too long, I'm going to keep using the prior example as the quote-unquote known power series. So I'm going to use this guy right here. This is my known power series. 1 over 1 plus 3x that we just created is my known power series. And what I want to do is let's find a power series for f of x equals, let's say, x squared over 1 plus 3x. All right, now what we're connecting to is this prior series, and in this case the easiest way for us to do this is to think of it as x squared times the 1 over 1 plus 3x power series that we know. So what I'm going to do here is I'm going to look at this as x squared times, and then what is my power series for 1 over 1 plus 3x? Well, we have that up here. We wrote that out. That was 1 minus 3x plus 3 squared x squared minus 3 cubed x cubed, so on and so forth. So that really is equal to x squared times our negative 1 to the n, 3 to the n, x to the n with our sigma notation. So x squared, come back here and scribble in front, x squared over 1 plus 3x has this power series representation. X squared times 1 minus 3x plus 3 squared x squared minus 3 cubed x cubed plus so on and so forth. Now check this out. All right, look how we can simplify this. And when I look at x squared times in parentheses this infinite polynomial, I know through the distributive property of multiplication that I can distribute x squared to every term in this infinite polynomial. So I can take x squared times 1 and get x squared. I can take x squared times 3x and get minus 3x cubed. I can take x squared times 3 squared x squared and get plus 3 squared x to the 4th. And then again, x squared times the next term gives me negative 3 cubed x to the 5th, and so on and so forth. So what I'm in essence doing, if I look at the sigma notation here at the end, I'm taking x squared and I'm distributing it through the sigma notation. So I'm going to take the x squared and I'm going to push it through the sigma notation. Now again, why is that legitimate? Well, because the sigma notation just represents a bunch of plus signs. So I took x squared and I distributed it over a bunch of plus and minus signs, the distributive property. So pushing the x squared into the series is completely legal because it's just distribution. So I end up with negative 1 to the n, 3 to the n, x squared times x to the n, and then just like we did with our polynomial and we distributed, right, when we multiply like bases, we add exponents. So when I multiply like bases, I add the exponents. So I have x squared times x to the n, and that becomes x to the n plus 2. Now again, I want to remind ourselves that we have just created the power series for the function x squared over 1 plus 3x, right? There's our power series. Okay. Again, that's what we're phrasing in this section, right? what is the power series for some function? Or in other words, what functions have a power series representation? And we now have, I've lost track, I think we have 5 of them that we've created. Now, every one of these series that we have created has been, in essence, algebraic manipulation. So we have taken a known series and we have, algebraically manipulated to produce another series. Now, there's another way that we could produce a series from a known function, and it's a derivative. So if we stop and look at this example here and then discuss this for a minute, and we'll move to another example. Look at my function x squared over 1 plus 3x. Can I take the derivative of that function? Absolutely. If I'm going to take the derivative of the function x squared divided by 1 plus 3x, I'm going to do the quotient rule, and I can find the derivative of that function. Now, is it legitimate to take the derivative of a power series? Absolutely. So if I come back up here to the line before, x squared over 1 plus 3x is equal to x squared minus 3x cubed plus 3 squared x to the 4th minus 3 cubed x to the 5th plus dot dot dot. So if I can take the derivative of the function, I definitely can take the derivative of its power series. Right? And if you think about this, right, this is just a polynomial. What's the derivative of x squared? 2x. What's the derivative of x cubed? 3x squared. What's the derivative of x to the 4th? 4x cubed. So when I differentiate a function, I can also differentiate its power series because I'm just differentiating an infinite polynomial. All right, now instead of using that function as an example, just quotient rules is going to get a little ugly. What I want to do is come back to our sine series. So remember back in the beginning we had sine of x equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot dot dot. And that was negative 1 to the n over 2n plus 1 factorial times x to the 2n plus 1. So I just want to come back to a series that isn't so nasty in terms of a derivative, to just talk about this concept with a little bit cleaner math. So here's the sine series, and the sine series has, here's the sine function, and the sine function has a power series representation. So I'm going to differentiate the left-hand side. Now if I differentiate the left-hand side, I'm taking the derivative of sine x. What's the derivative of sine x? It's cosine x. So I'm about to create the power series for cosine x. And I'm going to create the power series of cosine using the known sine series and taking its derivative. Now I'm going to talk through this and write this out here. So if I think of for a moment, right, I am taking the derivative of this infinite polynomial. So I'm going to take the derivative of x, and then I'm going to take the derivative of x cubed over 3 factorial. And I do not want to do a quotient rule here. So I'm going to take the 1 over 3 factorial off as a coefficient. And then I'm really differentiating x cubed. I'm going to do the same thing for the next term. X to the 5 over 5 factorial, I'm going to write as 1 over 5 factorial times x to the 5. And then, I would do the same thing for the next one, 1 over 7 factorial x to the 7th, and dot, dot, dot. So I'm running out of digital paper here. I'm really taking the derivative of, and I'm going to do my best to squeeze this in, taking the derivative of the series of negative 1 to the n over 2n plus 1 factorial x to the 2n plus 1. Ooh, look at that. I squeezed that in. Let me squeeze in the bracket. All right. So I've differentiated sine and gotten cosine. I'm going to differentiate the expanded terms of the power series, my infinite polynomial. And then I'm going to also differentiate the sigma notation of that power series. So when I differentiate this polynomial form, this expanded form, right, the derivative of x is 1. and then I hold the constant off, 1 over 3 factorial. The derivative of x cubed is 3x squared. And then the next term, 1 over 5 factorial times x to the 5th. The constant, 1 over 5 factorial, I pull out of the derivative operator. And then the derivative of x to the 5th is 5x to the 4th. And then the next term, I'm going to have 1 over 7 factorial, 7x to the 6th, and so on and so forth. Now let's think about the series representation, the sigma notation. Right? So what can I do with this derivative operator? Can I take this derivative operator and push it inside the sigma notation? Absolutely. Right? Because again, what does the sigma notation really represent? It really represents a bunch of plus and minus signs. So I already know the derivative of a sum is the sum of the derivatives, and that's what I just did with this polynomial. I took the derivative of each term. I in essence, moved the derivative operator inside all of the plus signs. So I'm going to push the derivative operator over here. So I have the derivative of the sum of terms. That's going to be the sum of the derivative of terms. Now I'm going to do one other simplification here. That negative 1 to the n over 2n plus 1 factorial is a constant. This is, 1 over 3 factorial, 1 over 5 factorial. So that constant, negative 1 to the n over 2n plus 1 factorial, I'm pulling in front of the derivative operator. That's just constant. And I'm taking the derivative of x to the 2n plus 1. So I'm going to write it that way for a moment and leave it there. Now I'm going to keep playing with this sigma notation on the far right hand side so I can catch up with where I am on the left hand side, right? So on the left hand side I already evaluated ddx, I already evaluated the derivative operator. I haven't officially evaluated the derivative operator here. So what I have now, I'm going to keep writing a little bit smaller. Cosine x is 1 minus, and I'm going to say 3 over 3 factorial x cubed plus 5 over 5 factorial x to the 4th minus 7 over 7 factorial x to the 7th plus dot dot dot, and that's equivalent to, I have negative 1 to the n times negative 1 to the n over 2n plus 1 factorial. And now I'm taking the derivative of x to a power. What's the derivative of x to a power? Well, I bring the power down and I take 1 away from the power. So I have my exponent of 2n plus 1. I bring that in front as a coefficient. So I get 2n plus 1 times x to the power of 2n plus 1 minus 1. Now in reality is plus 1 minus 1 cancels out, and I really have 2n here. Okay? X to the 2n. And I just noticed a typo on my work over here. Apologize. So when I simplify this expression, I should have x squared, not x cubed. I wrote x squared there. And then I wrote x to the 7th here, and that should be x to the 6th. We can see from the line above. And what helped me catch that mistake is when I look at this expression, my sigma notation, I really have x to the 2n. And 2n is all even numbers. Right? Anything that's a multiple of 2 is an even number. So all of my exponents should be even numbers. I caught that mistake real quick. And technically, here's my power series. This is my power series for cosine of x. But I can do a little bit more of cleanup. So before I move on to the cleanup, I'm going to stop for a second because this is the concept that we're discussing here. In the beginning of the video, we took a known series, 1 over 1 minus x, and we did algebraic manipulation, and we created a bunch of another series for different functions. So we had the function 1 over 1 minus x. We found a power series for 1 over 1 plus x through algebraic manipulation. And then we took 1 over 1 plus x. We created the function 1 over 1 plus 3x through algebraic manipulation. And what we have done here is we've taken the known series for sine x, and instead of using algebraic manipulation, we're using the derivative operator, and we've created another power series, this time for the function cosine x. All right, now let's finish this one off and let's do a little bit more cleanup and then we're done. And we're going to see something we would see in a textbook. Right? Okay, so I'm going to look at these coefficients here. So I have 3 over 3 factorial. Excuse me, I'm going to change colors here. Remember that 3 factorial is really 3 times 2 times 1. So to simplify this, I could cancel off the 3's, right? They kind of reduced out. And I end up with 1 over 2 times 1, which is 2 factorial. If I look at my next coefficient, 5 over 5 factorial, that's really 5 over 5 times 4 times 3 times 2 times 1. Similar, the 5's cancel, and I really end up with 1 over 4 factorial. So for the next coefficient, I don't want to have to write 7 factorial all the way out. Notice what's happening on this prior coefficient. The 5 factorial is really 5 times 4 factorial. So my 7 factorial, I'm going to really write as 7 times 6 factorial. And then the 7 in the numerator with the 7 in the denominator cancel, and I really end up with 1 over 6 factorial. So I'm going to clean those coefficients up in that manner. Now if I look at the sigma notation over here, let me come over here to the sigma notation, I'm going to do the same thing. When I come back to the constants, the coefficients, with actual numbers, what I did was I pulled off the first number and wrote the remaining in factorial form. So when I look at 2n plus 1 over 2n plus 1 factorial, what I'm really going to do is pull off the first term in the denominator, and then I'm going to write the remaining numbers in factorial form. The 2n plus 1's are going to cancel, and I'm going to have just 1 over 2n factorial remaining. And it's exactly what we did with those coefficients on the left-hand side. All right, so the little bit of cleanup that we just did there just gets rid of the coefficients, just makes them a little cleaner, doesn't get rid of the coefficients. So here's what we have. We have cosine of x being, we have 1 minus 1 over 2 factorial x squared. So again, up here, top of my screen, I have 1 minus this coefficient of 3 over 3 factorial, we simplified to 1 over 2 factorial times x squared. And then this next coefficient, we have 5 over 5 factorial that we reduced to 1 over 4 factorial x to the 4th. And then we have minus 1 over 6 factorial x to the 6th. X to the 6th plus dot dot dot, and then that's equal to the sum of, we have negative 1 to the n over 2n factorial x to the 2n. Alright, we got a little bogged down in some cleanup simplification there, but we have just generated a series for cosine of x using the known series for sine of x. And that's the bigger conversation in this section. We can take a known series, we can algebraically manipulate to create a new function in its power series. We can also differentiate to create a new function and its power series. Alright, so if we bring up Desmos real quick, I just want to take a second to show you this. If I plug in the function cosine of x, and then we plug in the expression that we have, so I'm going to put parentheses for my numerator. So I have negative 1, and then raised to the power of n, and times x raised to the power of 2n, and then all of that divided by, we had 2n and then factorial. Whoa, what happened there? Kind of weird extra parenthesis. 2n factorial. Right? I'm going to turn that off for a second. Turn off the series. So here's the function cosine of x. Here is my power series for that function. And if I add the first term, we have y equals 1 that approximates cosine. Again, not a very good approximator when I'm far from the origin. When I add the first two terms, I have 1 minus x squared. All right, I have a parabola. There's that parabola. And then when I add the first 3 terms, so here is, sorry about that, here is 1 minus x squared plus x to the 4th. And then there's that 4th degree polynomial. Now we're going to notice as we add more and more terms, the cosine function has a series that will converge for all reals. So this convergence spreads further and further and further for all reals. So what I want you to do for me is take a derivative and create a power series for a new function. So what I want you to do is we're going to come back and I want you to use the known series for 1 over 1 plus x that we had. Right? That was negative 1 to the n, x to the n. N goes from 0 to infinity. Right? So I want you to use this known series and I want you to take a derivative. Right? Take a derivative. So when you take a derivative, you're going to end up creating the function 1 over 1 plus. Actually, I'm going to want to say that. Hang on. I'm just going to let you do it and show me what function do you get when you differentiate 1 over 1 plus x, and then what is the power series that you get when you differentiate its power series. So pause the video, try that on your own. When you're done, unpause, and we'll talk about it together. All right, how did you do? All right, good. Sounds good to me. I heard everybody loud and clear. Let's do this together. So I'm going to rewrite out. So what I'm going to do is take the approach that I did on my series example with sine x. So I'm going to write out the first 3 or 4 or 5 terms. I'm going to expand out my polynomial. So I have from my known series 1 over 1 plus x is 1 plus x. Excuse me, that alternates. It's 1 minus x plus x squared minus x cubed plus x to the 4th plus dot dot dot, and that is what we already wrote, negative 1 to the n, x to the n, as n goes from 0 to infinity. So there's my sigma notation. So what I want to do is take the derivative here. So I'm going to take the derivative of the function and in turn take the derivative of the expanded version of the power series and then take the derivative of the sigma notation version of the power series. So I am going to take the derivative of 1 over 1 plus x. I'm going to do a little bit of side work here. A little bit of side work. So when I take the derivative of 1 over 1 plus x, what I'm going to do is write that as 1 plus x to the negative 1 power. And then I'm going to differentiate this expression, and that's going to be negative 1 times 1 plus x to the negative 2. So I end up really with negative 1 over 1 plus x quantity squared. So when I differentiate 1 over 1 plus x, I'm going to then differentiate its power series. So I'm going to scroll down here just a little bit. So I have negative 1 over 1 plus x quantity squared is going to be, so I'm going to take the derivative of the expanded term. So I'm going to go ahead and write that out. Right? I'm going to say I'm taking the derivative of 1 minus x plus x squared minus x cubed plus so on and so forth. Right? So I'm going to be taking the derivative of, in sigma notation, negative 1 to the n, x to the n as n goes from 0 to infinity. Now, just like we talked about with the sine series, when I differentiate a polynomial, I'm just going to differentiate each term. Right? So the derivative of a sum is the sum of the derivatives. So let me differentiate each term here. So the derivative of 1 is 0. Right? The derivative of negative x is negative 1. The derivative of x squared is plus 2x. The derivative of negative x cubed is negative 3x squared, and so on and so forth. And then when I differentiate my sigma notation version, again, remember the derivative operator moves inside the sigma notation because that just represents a bunch of plus signs. And then negative 1 to the n is not the x variable, right? My differential operator is on the x. So negative 1 to the n is just representing plus minus, right? Those are just coefficients, and I'm differentiating, x to the n. So I scroll a little here. So I have negative 1 over 1 plus x quantity squared. Right? And I'm going to eliminate the 0 here. This is negative 1 plus 2x minus 3x squared plus so on and so forth. And then negative 1 to the n times the derivative of x to the n is bring the power down and take 1 away. And there's my derivative. So my series for negative 1 over 1 plus x squared has, right? So my function, negative 1 over 1 plus x squared, has this series representation. Negative 1 plus 2x minus 3x squared plus so on and so forth. Now let me show you something. I'm going to do a little bit of cleanup with this sigma notation. If I plug in n equals 0, I'm going to get 0 times x to the negative 1. So 0 times anything is 0, right? So when I plug in n equals 0, here's the first term that we cleared out. We deleted that 0 from the derivative of 1. So when I delete this 0, it's redundant, so why write it? Instead of having the n equals 0 term here, I'm starting at the n equals 1 term. So to just make this look a little cleaner, I'm going to start my series at n equals 1. So I'm going to have negative 1 to the n times x to the n minus 1. So this is a cleaner version, just eliminating the 0 that's in that series. So now when I plug in the first term, n equals 1, because see, I'm going to get negative 1 to the n, which is negative 1. You can see that first term, and then 1 times x to the 0. So plugging in 1, I get 1 times x to the 0. X to the 0 is 1. So negative 1 is the very first term when n equals 1. And then when n equals 2, I get negative 1 squared, which is positive. 2 times x to the 2 minus 1, which is x to the 1. So positive 2x, there was the next term in my power series. So negative 1 over the quantity 1 plus x squared. This function has this power series representation. So we developed this new function by taking the derivative of a known function. We developed the power series by differentiating it as well. So through algebraic manipulation, we can create power series of other functions. Through the derivative operator, we can create power series for other functions. Now, the last thing I want to talk about is integration. So if I can use a derivative to create a series for a new function, I definitely should be able to do the same through integration. All right, so for this example, let's stick with that nice clean example, a nice clean function that we just manipulated. Let's look at 1 over 1 plus x. And again, this is our known series, 1 minus x plus x squared minus x cubed, so on and so forth. Right? And that was negative 1 to the n, x to the n. So we're using this as a known series. And what I want to do is integrate. Let's integrate the function. So I'm going to write an integral here. I'm going to get a little sloppy. I apologize for this. I'm going to integrate the function 1 over 1 plus x, which means I'm going to integrate its power series, which means I'm going to integrate the sigma notation of its power series. I'm going to do an antiderivative of my function. Now, if I take the antiderivative of 1 over 1 plus x, I get the ln of absolute value 1 plus x. And then when I integrate my infinite polynomial, for this example, the integral of 1 is x. The integral of x is x squared over 2, right, or 1/2 x squared. The integral of x cubed is, 1/3 x cubed. Integral of x to the 4th is 1/4 x to the 4th plus so on and so forth. Now, just like with the derivative operator, the integral can push inside the summation symbol. Right? And again, the reason for that is the integral of a sum is the sum of the integrals. So I'm going to sum my integral. And I'm going to come back and erase that. Don't write that down yet. So when I do this integral here, right, the negative 1 to the n is constant. Right? Now, I'm really integrating powers of x. So let me do a little bit of erasing, and I'm going to pull that constant of -1 to the n out, and I'm going to integrate the x to a power. So when I integrate x to a power, how do I evaluate that? Well, like we just did, we add 1 to the power and we divide by the new power. So the integral of x to the n is going to be x to the n plus 1 divide by n plus 1. So there's me adding 1 to the power and dividing by the new power. All right? So let me just kind of recopy all of this down. So the function ln of absolute value 1 plus x has a power series representation. And it's x squared over 2 plus, x cubed over 3 minus x to the 4th over 4 plus dot, dot, dot. And here's its sigma form of that series. Now again, if I plug in n equals 0 into my sigma notation, I get -1 to the 0, which is positive, and then I get x to the 1 over 1, and that's my first term in my infinite polynomial of that power series. And I could keep plugging in n equals 1, n equals 2, and we would see this generation here. So I can differentiate a function and differentiate its power series to create a power series of some other function connected through the differential operator. I can also integrate a power series. So in this section, I'm going to do another example or two, but in this section, the conversation seems like every function has a power series representation. Now we took the known series for sine and differentiated it and developed a series for cosine. We took the known series for 1 over 1 plus x, integrated it, and created a series for ln of 1 plus x. And then we did some algebraic manipulation to do the same, right? So officially we started with 1 over 1 minus x. We did algebraic manipulation to get the series for 1 over 1 plus x. So what we're seeing so far in this section is we can use algebraic manipulation, differentiation, and integration. I think I've said that probably 5 times at this point. But that is the main conversation here. A couple other things I want to talk to you about but that's the main conversation. Now the question that you might be asking is, what if I want a power series for something like e to the x? That's a really good question. I'm glad that you asked it. Well, here's the issue we're going to kind of see in this section. I'm going to point this out to you. There's no way for me to take the function 1 over 1 minus x and get to the function e to the x. There's no way for me to take the function sine x and get to e to the x. Can't do algebra, can't do derivative, can't do integral. So in the next video, what we're going to ask is, how do we find the series for any function that I want a power series for, like e to the x? We'll take a look at that shortly. So be patient, be patient. I know you're excited. I know you want to hear that answer. We will get there soon. So one last thing I want to discuss with you in this video. So what I want to discuss with you is what you would typically see in the textbook, and it is the generic representation of the conversation that we just had. Now, we just had a conversation that we could algebraic manipulate, differentiate, integrate, but we've looked at specific examples. So let's take a look at the conversation in a general form. So what we actually discussed in the prior video was that a function having a power series representation, we could write as c sub 0 plus c1x plus c2x squared plus c3x cubed plus so on and so forth. So in a sigma form, I could have c sub n x to the n as n goes from 0 to infinity. So this just says that a function has a power series representation. The c sub 0, c sub 1, c sub 2, c sub 3 are just whatever the coefficients are. And then we have x to powers. Now I'm going to scroll back up for a second and just point out to you that for this ln function we just created, the c sub n's are -1 to the n over n plus 1. Those are my coefficients times powers of x's. If I scroll back up, this is really slow. If I scroll back up to the -1 over 1 plus x squared, my coefficients are -1 to the n times n. times powers of x's. I scroll back up a little further and we look at, where was it, cosine. So when I look at the cosine series, its c sub n's are negative 1 to the n over 2n factorial. So each function has coefficients times powers of x's. And that's really what this generic version is saying to us. Where am I at? All right, so that's really what this generic version is saying. Every function has a power series representation, and in general, this is what it looks like. Now, this function only has a power series representation on the interval of convergence. Right? So this is going to be true for some interval. Right? For some interval of convergence. And remember, we had introduced the term in that prior video that the interval convergence had a radius of convergence, right? So we use the term radius of convergence. So whatever that radius of convergence is, let's call it capital R, some number, capital R. For the sine and the cosine series, I converge for all reals, so the radius is infinity. For the 1 over 1 minus x series, that series converged from minus 1 to 1. So its radius was 1. And the way I like to think about this is I'm on a number line. I'm going from minus 1 to 1. The diameter is 2. So the radius is the distance from the center to the endpoint. So there's a radius of 1. So whatever that radius is, right? We have a series, we have a function that has a power series and it converges somewhere. Whatever that interval is, its convergence is R. Now, what we can do is we can move the center of the series. And when I think of the sine series or the cosine series, let me bring my graph back up real quick. When I look at the cosine series, remember the convergence began at 0. And the convergence spread from there. If we go back and we look at the series for sine x, we see the same behavior. If we go back and look at the series for 1 over 1 minus x, we see that same type of behavior. And that's because the series was centered at x equals 0. Now when we look at this generic form, that's what we really have. We have basically like x minus 0 to the first power, x minus 0 squared, x minus 0 cubed, and in general, x minus 0 to the n. So we can write in an even more general form that a function has a power series centered anywhere we want to center it. So I would write c sub 0 plus c1 x minus a plus c2 x minus a squared plus dot dot dot. Right? So we'll have coefficients, and then we can center the series anywhere we want. So this is a power series centered at A. Let me clean this up a little bit. Now again, we centered all of our series at 0 so far, right? We had just x to the n, or x to the 2n, or x to the 2n plus 1, right? So each of those series we looked at were centered at 0. So again, when I graph them, the convergence begins at 0 and then spreads from there throughout its interval of convergence. So this is going to have, a radius of convergence of R. So in general, this is the most generic version of a power series. So we have a theorem in this section that basically says I can take this power series and differentiate it, and I can take this power series and integrate it. All right, I paused the video real quick. I did a screenshot out of Stewart's calculus textbook, and there's theorem number 2 in this section. And basically what theorem number 2 says is what I've said 5 times up to this point in this video. And that is a function will have a power series representation centered at A. So its radius of convergence is R. So here's its radius of convergence is R. Now, I can differentiate my function, and therefore I can differentiate that power series. And think about what we do, right? When we take the derivative, The derivative of x squared is bring the power down, take 1 away, and that's what we see right here on this term. The derivative of c sub 2 times x minus a squared is going to be 2 times c sub 2 x minus a to the first. So anytime I differentiate a function, I differentiate powers of x. And there's that expanded form, right? My infinite polynomial. And if I look at the sigma notation, x minus a to the n, in general, bring the power down and get n, x minus a to the n minus 1. So I can have a function that has a power series representation. I can differentiate to generate a power series for a new function. And then I can integrate. So I can integrate my function and do the same thing. Now, if we look at the integral expression, right, I'm going to integrate f, and here I have the integral of f, so whatever that function is. And then I'm going to integrate the power series, and again, integrating x minus a squared is going to be 1/3 x minus a cubed. And in general, x minus a to the n is going to be x minus a to the n plus 1 over n plus 1. So add 1 to the power, divide by the power. Now, something that I glossed over and ignored in our two examples is what I want to point out to you here. Remember that when we integrate a function, we always get an arbitrary constant of integration. So technically, in the most general form, we have a constant of integration out of that integration process. Now remember that constant can be anything that we want it to be. Right? So the arbitrary constant represents the family of antiderivatives, but for any value of c, that antiderivative is true, and so what we typically do is we choose that constant to be 0. So if you look back at the example that we had up here, when I did the integral, I had a constant of integration there that I didn't write. So the integral of 1 over 1 plus x, I technically have a plus c here, but I didn't even mention it. But what we're going to typically do in practice is choose that constant to be 0, and we just don't have the plus c. Now again, technically we do have the plus c, but we're going to typically choose c out of convenience to be 0. Now what the other thing this theorem says is really cool. So whatever this power series is that we started with, we either differentiate or we integrate. These new series, the derivatives series or the integrals series, is going to have the same radius of convergence. So for example, my sine series had a radius of convergence of infinity. Its derivative, the cosine series, has the same radius of convergence of infinity. Now your example that you integrated, or I guess we did it together, we integrated 1 over 1 plus x. The series for 1 over 1 plus x had a radius of convergence of 1. So through integration, that new series for ln is also going to have a radius convergence of 1. So this theorem is really cool. Says two things to me. I can differentiate and integrate a series, and the radius of convergence won't change through either of those processes. Now something you will probably notice in the homework, or maybe you won't. When I differentiate, I sometimes lose convergence at the endpoint. So for example, let's suppose my series converge, so my original function converges on the interval, let's say minus 2 to 0, all right? So let's say I have some power series, here's its interval of convergence. Now this is a radius of 1. Right? Because to go from minus 2 to 0, that's a distance of 2. Half of that is the radius. Now, if I differentiate through a derivative, most likely, not always, most likely I will lose convergence at the endpoint. So I could see scenarios like that. But the radius doesn't change. The radius stays the same. So whether I differentiate or integrate, radius stays the same. Now, let me come back up here. Here's my interval of convergence for some function and its power series from minus 2 to 0 inclusive of the 2. When we integrate, not always, but sometimes I can pick up convergence at an endpoint. So let's suppose at x equals 0, I pick up convergence there. Whether I pick up convergence or lose convergence, it's still the same radius of convergence. So this theorem is basically saying don't dwell on convergence at the endpoints. The radius will be the same whether the endpoint is included or not. All right, so this video is getting pretty long, but I want to do one last thing, and this isn't something you would really see in this section of homework, but I want to add a little bit of motivation of what we're doing here to kind of keep our eyes on the big picture, the big prize. Now, what I'm about to show you will actually take deeper in the next video. I'm going to do a little bit of foreshadowing here. So what if I wanted to integrate the function sine of x squared? So if I look at this integral back in a chapter where I have techniques of integration, there is no antiderivative I can do here. There's no technique that would work. I can't do u sub. I can't do by parts. None of those techniques would work. So how would I evaluate this integral? How would I estimate or approximate this integral? So in this section, here's how we're going to discuss that. So we're going to say, well, we know that sine of x has a power series of x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, minus x to the 7th over 7 factorial plus dot, dot, dot. Right? So here's the expanded version of my power series. So I could do algebraic substitution. So the sine of x squared is going to be the input and then minus the input cubed over 3 factorial and then plus the input to the 5th over 5 factorial and then minus and so on and so forth. Plus dot, dot, dot. If I clean this up a little bit, right, what I really have here is that sine of x squared. And I'm going to go ahead and say approximately. So let's say I use the first 4 terms that I have here. Sine of x squared is approximated by x squared minus, I'm going to write this as 1 over 3 factorial x to the 6th plus 1 over 5 factorial x to the 10th minus 1 over 7 factorial x to the 14th. And I'm going to stop. I'm not going to say plus dot, dot, dot because I'm only going to use the first 4 terms to approximate sine. Now, what we were doing in my beginning of this example, this foreshadowing, is we were trying to integrate sine of x squared. So we can approximate that integral with the integral of its power series. So instead of integrating sine of x squared, which we don't know how to do through techniques of integration, we can instead approximate the integral with the first 4 terms of power series for sine of x squared. Now what we'll see in the next section is we'll have limits of integration here. We might be integrating from 0 to 1, but I'm not going to do that here. Right? We'll do that detailed in the next video. But this is a good approximation. This is actually going to be a really amazing approximation. So if I go ahead and evaluate this integral, just the last step of the antiderivatives. Right? So this is, 1/3 x cubed minus 1 over 3 factorial x to the 7th over 7 plus 1 over 5 factorial x to the 11th over 11 minus 1 over 7 factorial x to the 15 over 15. So here's an approximation to the integral of sine of x squared. If we were to use this to actually do an estimation from the integral of 0 to 1, we could estimate the error. This is an alternating series, so we have the alternating series estimation theorem. So we could estimate the error here, and we would find out the error is really tiny. It's minuscule. So using the first 4 terms of the series is an excellent approximation to integrating the actual function sine of x squared. All right, I don't want to get ahead of myself. We will officially do that in the next video. But I just want to give kind of a bigger picture perspective here, that we are going to use power series to estimate functions, and we're going to have some real advantage to doing that. All right, I'm done. This is a long enough video as it is. I will see you guys in the next video.